All right, second time is a charm. Use press button. We didn't hear our first one. Welcome to the 9th edition of our purely remote, again, Rust Meetup Munich. I'm really happy that you're here again. Today we have 2 talks, but before that, our host will give a few introductory words.
Yeah, it's too much sound now. Is it too loud? Okay, hi everyone. You can hear me now? Yes, too loud, or it's okay? I hope it seems like it's working now. I started before saying that I tried to keep it short to not bore you too much and get to the interesting talks. And now I should keep it extra short because you already had to watch us say nothing for a while. My name is Timon. I'm one of the co-founders of Luminovo. I was saying before, this is, I think, the first time I can remember that I'm actually a little bit unhappy that we're not spending more of our company money because the original plan of sponsoring this event was to have a nice in-person event with lots of people, lots of pizza, lots of beer. Now it's a little bit reduced due to COVID. I hope that maybe next year, post-COVID, if that will ever happen, we can have a proper in-person meetup that maybe we can sponsor again. Just very shortly about Luminovo, we are a software startup based in Munich, but fully remote. At this point, we're building software for the electronics industry. Specifically, that means we try to close the feedback loop between people that design electronic products. That means everything that has a printed circuit board in it, and the physical manufacturing or assembly process. So we want to build software that on the click of a button gives you feedback about how much it's going to cost, how long it's going to take to actually build and assemble your printed circuit board assemblies. We went with Rust from the very beginning. So a year and a half ago, we got started on our product journey. Wanted a statically typed language, was between Rust and Go back then. And we had one big Rust fanboy at the company that convinced me to go with it. And I think we haven't looked back. We enjoyed it a lot. So at this point, we have 4 teams, 3 of which write most of their code in Rust in the back end. And yeah, that's it. I think I'll hand over now. I'll probably post a link to the open positions that we have at Luminovo in the channel. And later on, go have a look. We're looking for both senior, but also new talented engineers that are new to Rust and want to help us put a dent into the electronics industry. Thanks a lot. And I'll hand it over to, I think, Felix now. Thank you.
It's good, Phil. Okay, thank you. I'm talking a little bit about Tokio and especially about the mistakes you can make with Tokio. Or in other words, I will talk about some of the mistakes I made in the last 5 years. Maybe first of all, a small disclaimer. Everything I will show you is documented. And if you read the documentation, you wouldn't make this mistake. So, but here's the short story about it. Very short about me. I'm Felix Umuber. My GitHub handle is at felixo, or you can write me an email, felix@umuber.de. I'm a Rust developer working at ESR Labs / Accenture. We are doing software for cars, mainly Linux boxes and cars. And I'm fully vaccinated, and I hope you too. Okay, let's start. Tokio. Short recap, what is Tokio? Tokio is a I/O framework, let's name it like that, where you can drive async code that is mainly doing I/O operations. So Tokio is built for handling sockets, for handling protocols, and combining streams and futures, and do I/O bound operations. So that's the main set of Tokio, and almost every serious network application today is nowadays normally based on Tokio. So Amazon is putting a lot of effort into Tokio. They also hired some of the Tokio guys. And here we see some examples from the Tokio website, which is tokio.rs. On the left side, we have a short main. You see this Tokio : main macro on top, which is basically some shortcut for saying, okay, please run, execute this main function within Tokio executor with defaults. Defaults means that we have an executor that is spawning a thread pool. The thread pool has normally the number of threads as you have CPU cores. That's the default. And then you can do fancy stuff as you see below. For example, here's some client connect, and there's this magic await in behind, so probably everyone knows what that means. Because client connect is returning a future, and we are awaiting the future until it completes. And every operation we see here is driven on the thread pool that is started by Tokio. And we basically just don't know on which threads it's running and what happens in there. And that's where we come to a couple of problems. Tokio has a lot of features. You can do UDP, TCP, and file I/O, and receive Unix signals and whatnot. But what we talk about today is mostly about all this task and threading things that Tokio comes with. For that, we only need to know that one important thing, what a Tokio task is. A task is something that is executed somewhere on the executor. So for the mental model, you can think about it, treat it as a thread. So it spawns some then, and then it runs until it completes. That's basically everything you need to know about a task. Here on the right side, we see that we spawn two tasks. The first is sending something on a one-shot channel. One-shot channels are Tokio specific. So in the standard libraries, there are no one-shot channels, but it's kind of comparable to the channels from the standard library, if you know that one. Okay, tasks. The first thing that can go wrong with tasks in Tokio in general is panics, as easy as it is. Here on the left side, we see again some code that spawns two tasks, and one of the tasks after 5 seconds will panic, will crash. I did that on purpose by unwrapping a none. And what happens underneath is, when we run that our program will execute, and when it hits this unwrap, the thread where this task is executed will panic. But the result is that task panics, and that thread panics, but everything else continues running. Means if you do not something else to handle that specific situation, you will end up with okay, some task panicked, it's ended. Tokio will replace the threads that panicked, but if you don't take attention to your logs, you will never notice that you had a serious problem somewhere in your code. There are a couple of solutions to that problem. The complicated problem is that you install custom panic handlers. You can do that. I normally tend to just add something to the cargo manifest to say, okay, on a panic, please just abort. And this will abort the whole process. And with the setting, you can catch panic even in the Tokio executor. Happens from time to time because it's quite easy to start along with a Tokio program. You just need to throw in Tokio into your dependencies. You add this handy Tokio main macro on top of your main, and that's it. But if you don't think about anything else, you will sooner or later run exactly into that problem. But that's not all. Next, blocking threads. As said before, Tokio drives a thread pool, and our tasks are executed on a random thread on that thread pool. This scheduling of the tasks is done in a cooperative way. That means if one of the tasks doesn't return or is in an endless loop, you're blocking that thread forever. This is quite easy. This is not a major problem if you do that like that, if we see it here. For example, we're just doing a sleep, which is a blocking operation. So we are returning control to the operating system for 1 second, and then after 1 second, we are continuing our operation. But within this second, nothing else can be executed on that task. Means if we are doing that in the number of tasks as we have threads, we are blocking the whole executor, and nothing else get produced, processed. This is the easy approach, the easy version of that problem, because here nothing bad happens. The next slide is also a little bit more complicated, but in the end, it's the same problem. We see that we are spawning 8 tasks on the bottom that are just sleeping with an STD thread sleep, which is a blocking operation. And on the top, we are just printing some random stuff every second. And what we see is if we execute this piece of code where we are printing the thread ID on every print, that actually the code just runs on 2 threads. Because we are starting our Tokio runtime, the executor, with 10 threads in total, but 8 threads are permanently blocked by our blocking sleep from this 10 tasks spawned below. And we see the execution only runs on 2 threads. This is something you probably don't notice from the beginning because your program works. It just won't work as the performance you expect. Even under full load, you won't see that your CPU is fully used because it's just using 2 threads and not the 10 you configured. And that's something that's not so easy to discover because everything works. Wait. There's a handy thing in Tokio which is called spawn blocking and block in place. So the Tokio guys did take care for that situation that we want to execute blocking code within our async environments. It's a very common thing. So for example, you have to do a system call in IO control, or you want to, don't know, use a library that is not async and needs to block someone. There are 2 methods. The one is spawn blocking, which is spawning a new thread, putting the workload you want to spawn into that thread, and when this code is executed and finished, then the thread is terminated later on after a specific timeout. The next thing is block in place. Block in place is intended for shorter blocking operations where you don't put the execution on a dedicated thread, and you block the current set of the executor, but the runtime marks the thread as a blocking thread and will spawn new threads if needed. But this doesn't solve the problem because you can still block your runtime threads because the spawn blocking will block the whole task you are executing the block in place. Sorry, not the spawn blocking, the block in place. Here we see a short example. We have a loop. We are doing a select. We have 2 intervals. An interval is a structure where the tick function returns a future that completes every setup after each setup duration. So we have a fast tick every second, and we have a slow tick every 10 seconds. And what we see here is within the select, somewhere our slow tick will be ready. Then we execute this block in place. We perform this thread sleep for 60 seconds, which blocks the whole task. Means we don't execute the fast tick, even when we execute our blocking thread sleep within this block in place operation. Again, this is something that is documented in the documentation of block in place, but I read it too late. In this example, it's quite easy because you see, you're doing that wrong. You're doing a blocking operation within a select, easy. But if you have a non-trivial application and you're calling something and you don't know what you are actually calling, then you might hit a blocking thing, a block in place within from a select or join or all that functions. But it can be even harder. You can call something from a library and you have no idea what it's doing. Here I just took a random example from the Redis client. Here it's kind of obvious that it might probably block because Redis does TCP and whatnot, and this is probably a TCP connect, and TCP connect is a blocking operation. So here, if you're writing such a line of code in an async block, you probably should be scared because, does this code block or not? In this example, it's quite obvious. The code will block, for sure. But what if you're calling something where you don't expect it to block? And until today, we don't have something like annotations on functions. Okay, this function can block, and it's not so easy to find out what actually will block or not. And yeah, so that's why this is probably the biggest problem, that you are doing something what you actually don't know what happens behind after you do a specific call. But enough about blocking. Let's talk about threads. First of all, again, Redis has an async API, so you don't have to use this blocking call. You can just use the async API from Redis. Let's talk about threads. At the beginning, I said that Tokio runs on a thread pool, which is pretty cool because today everything runs on a thread pool. We don't want to have more threads than CPUs. That's a common thing that everyone knows, that the performance will probably decrease if you spawn thousands of threads just because you want to perform thousands of operations in parallel. But you have to keep in mind what the costs of a thread are. And a colleague of mine posted this graph some time ago with the relation between, for example, a memory write and a thread context switch, which is by far more expensive. And that's something we have to keep in mind when we are now combining blocking operations with dedicated threads and our normal thread pool. The first problem we have with Tokio and those threads that we actually don't know how much thread we spawn. Here, very easy example. So we are calling 20 times Tokio task spawn blocking, which will take the code in the closure path to spawn blocking and put it in a new thread that is started by the Tokio executor because it can block. You said, okay, I'm running something that can block, so please put it in a thread where it's allowed to block. What happens is that we spawn a lot of threads. Even when we just don't expect that we have a lot of threads and stuff because we are using this async code and we're just using the spawn blocking, but you have to keep in mind that every spawn blocking operation will or might create a new thread if there's not just one around which can be used.
Is there a bound to the number of threads that can be created?
Probably yes. I don't remember. I have to take a look at the documentation.
Or you could just out of memory, I mean.
Probably there's an upper bound for the number of threads. It can get even worse if you're using the Tokio FS module, which is pretty handy because you get the same API as in the standard library, just in an async version. So for example, there's an FS file open, there's an async read, there's an async write, so it's the same as stdio read and write. But this needs to be used with care because underneath it's basically a wrapper around the std FS module with block in place or spawn blocking blocks around the blocking operations. That means this code here, how many threads will we spawn? A lot of, because for every Tokio FS operations that normally would block, we are actually spawning a new thread if there's not one around in the thread pool. And that's something that is also not quite obvious if you just take, oh, cool, there's Tokio FS. I can get a future here and pass the future around and map it and can do a lot of cool things with it. But you have to keep in mind underneath, you're still using this spawn blocking or block in place, which in case it can be created a new thread. It can be possible that a new thread is created, and that's a very, very expensive operation. There currently is an attempt to support U-ring in Tokio, which works around this problem, but I think it's not yet production ready, but I don't actually know in detail. Another thing that hit me hard are the thread timeouts. We've seen before that Tokio is starting thread on request. So when it is in full load and you request a blocking operation, Tokio will start a new thread for it. But those threads don't live forever. There's a default timeout of 10 seconds. And after 10 seconds, the thread is stopped. This timeout is there to avoid that if you have 10 block in place operations after each other and you don't want to start a thread for each operation, stop the thread, start a new thread, so the threads are kept running for 10 seconds, and after 10 seconds, they're actually stopped. And here I added a small print when the thread is stopped. So what you should never do in Tokio is use something like thread local, for example, that will not work. For me, my problem here has been that I used a system call which applied to the current thread, which is quite stupid if you're running on a thread pool. And then I got confused why things didn't work when the thread got terminated, and I needed some time to figure out, oh yeah, I did the system call from a thread, and 10 seconds later something bad happened because the thread was stopped. Yeah, something you need to know. Another point where you can run into problems very easily are this from std methods for file and TCP stream and UDP socket and so on. It's quite handy. You can convert a std.fs file or an std.net TCP stream, for example, into a Tokio variant. What happens here is that it just takes the file descriptor, which is so std.fs file is basically a wraparound integer in file descriptor. And what it does, it just converts it, but it does nothing else. And what a file descriptor needs to be used properly in Tokio is that it needs to be set to non-blocking. If you don't do that, you have a Tokio FS file, for example, and you have a file descriptor within this Tokio FS file, which is not set to non-blocking. That means that sooner or later you will, when your program receives more load, you will get from an operation on the file descriptor, you get an error E would block. And this is something that is oh no, sorry, the other way around. You never get this E would block, your operation would just block. So you're assuming your TCP stream write is a non-blocking operation, but with this file descriptor, the socket you're passing into the TCP stream is non-blocking, is blocking. You have a blocking operation even when using the Tokio struts. What you have to do is you have to convert the FD and set it to non-blocking before you pass an std.fs file or std.net TCP stream into a sysfrom std methods. Also something that is in the documentation, again, the behavior here changed with Tokio 1.5, something like that. Before they did within the from std functions, they set the file descriptor to non-blocking, but that behavior changed recently. And yeah, also something you don't see from the beginning when you do the mistake, because you need some load for discovering that. Not really a problem, but something very fancy I want to give you a pointer is the Tokio console. That's a quite new project the Tokio guys are developing currently. This is an extension to the runtime where you can connect a TCP client. I think it's gRPC interface between the runtime and the client. Here we see this console client where you can get a top-like view on the Tokio tasks. So normally from a top, you have your processes and threads and whatnot. And here we can see, I get an overview about all the tasks I'm executing on my executor. And if you have a look at the API of Tokio, you can see that you can also name tasks if you want to, and here you get a couple of nice statistics about the tasks you're actually executing. This helped me in the past a lot to find certain problems with blocking tasks, with tasks going mad under some circumstances and so on. Okay, that's all. Thank you for listening. Hope you heard something new. And there's a question from our small audience.
So I'm curious if you can share your thoughts and your experience around one thing that happens when you do a lot of async code is kind of contagious, right? Because you have to at least so I'm not a Rust developer, but at least in JavaScript, when you have things that are asynchronous and you want to call them, your code kind of needs to be called from asynchronous unless you want to block, right? So you kind of end up being contagious. Do you know what I mean?
Not yet.
So you have to make more and more code asynchronous to kind of keep being asynchronous.
Yes.
So I'm curious if you have any thoughts, or do you find it like a problem at all? And the other thing I wanted to ask you is whether, like, I got kind of like the impression that the macros make some of these errors like more likely for beginners, because you just think like, oh, this is nice. Whether you think like whether they're actually a little bit dangerous and people should just use like direct APIs or whatever they're called.
Depends. So the question. So the question is about whether it's a good idea to use the Tokio provided macros because they hide maybe some implicit things. Is that correct?
Yeah.
Yeah. So for this Tokio main macro, this is definitely true. This is quite easy to put in that macro and you are done setting up the runtime, but you get defaults. If you're happy with the defaults, everything is fine. But normally, if you're writing a serious application and not just a toy, you will end up in setting up your own executor. You will configure it with thread numbers, with thread names and things like that. And normally you also will have to do things before you start the Tokio executor. So for example, you want to set up logging, or you want to, don't know, enter a namespace, or things you don't want to do from the executor. So for example, again, something that hit me hard is entering a mount namespace. When you do that, that applies only for the current thread. If you do that from running within a Tokio executor, actually it's just one thread, but not the other threads. And that's obviously a bug. And
how did you solve that?
I did solve that by executing code before I set up the executor. So not using this Tokio main macro, but executing some code, then firing up the executor and switching to the async code. No.
I can ask another question. Sounds like you had a lot of these problems you encountered, like when writing code. I was wondering what kind of techniques have you learned to debug this? So you mentioned, for example, it's Tokio console, and there's like other things or tricks that you kind of now used to when you encounter similar bugs.
I don't know. So I looked a lot at thread IDs. I don't know. So I didn't use anything specific for debugging those things because normally you get some behavior. It's not. We have two kind of failures. The first kind of problem is that the performance decreases because you're blocking a lot of things and you don't make progress somewhere else. That's something where you see, okay, I'm under full load, but my CPU is not under full load. Where's the problem? And then you just start searching, where's something not going right. Some of the failures also pop up if you put even more load on the system. That is something when you see that, okay, this call should not block in theory, but I have more load on my TCP socket or whatnot, and then you get blocking conditions you don't have when you're running the software on your desktop on the testing, but when you put it to production, you have more load, and then you see, okay, here's something wrong because it doesn't perform well. But besides this Tokio console, I don't think there's something you can really do here. Maybe the tracing crate might help here, but I haven't tried that.
I have another question about the Tokio console. Is it like, do we have the Tokio console? Is it just like, is that software which per default can examine like the processes and tasks and then sees, okay, there's a Tokio, there's like a spawn thread there, or is it something that you have to enable from your Rust code?
The question is if the Tokio console works out of the box or you have to set it up. You have to set it up. Today you also need, I think, to enable some nightly features. So it's not something that you just turn on, but there's an example on the homepage you can follow. It's quite easy. Thanks a lot.
Thank you.
So. Den kann man dann zum Schluss erst zuschalten.
Okay.
Take it away.
Okay, all right. Oh, hi, I'm Rahix, and I'm going to talk about embedded Rust, and specifically a little project I made with embedded Rust. So I'm using Linux, and for any Linux users here, you'll know of Pulse Audio probably. Pulse Audio is the de facto standard audio mixing software in desktop Linux. So it manages audio streams from applications and mixes them down and then sends them to output devices. And there's a nice tool for controlling Pulse Audio. Looks like this. This is Pavu Control, where you can set the volumes of different applications, mute them, set what output device an application should go to. And this is great, but I like this. So this is a hardware mixing console, what's used in big audio studios, and this feels really nice. You get real hardware when you want to set a volume, for example. You have a real fader you can move, and this is much more fun than having to open some GUI and click some sliders. And so instead of having to use Pavu Control, I wanted to integrate something like this into my setup. Of course, this one is a bit too big. So instead, I scaled it down slightly, built my own version. It looks like this. This is my Pavu mixer. It has 4 channels for applications and then 1 main channel on the right. The application channels, they get mapped to different programs running on my computer. You can see there is a small display with icons of what application is currently mapped to a channel. Then there's, of course, the fader for setting the volume. Beneath the display, there are mute buttons for quickly toggling the mute of a channel. And then for each channel, there is a level indicator. So for the 4 application channels, the LED over the fader will blink or in sync with the audio that's currently played on that channel to indicate that there's some audio stream currently running. And for the main channel, there's this bar graph displaying the level of the main audio output. So I've built this with Rust. And in this talk, I'm going to introduce you to embedded Rust and then show how I used embedded Rust to build this project. First of all, let's talk about embedded. What is embedded? Embedded is a very broad topic. It's impossible to condense down into one sentence, I think. But in most situations, we're looking at some microcontroller that's embedded into a larger system. And on this microcontroller, some firmware is running. And for most embedded systems, this firmware is the only thing that's running there. So in contrast to a desktop or server system, there is no general purpose operating system running beneath our application. And this is also called bare metal sometimes. So our application is the thing running directly on top of the actual hardware. Now, this chip is called a microcontroller, and this microcontroller is where our firmware is running. Inside this microcontroller, there's a CPU. In this case, the microcontroller I'm using in this project is an STM32F3 microcontroller, and it contains a 32-bit ARM Cortex-M CPU. But a microcontroller is much more than just a CPU. First of all, next to the CPU, the microcontroller contains memories. So there's flash memory, as you can see, 256 kilobytes in this case. Flash memory is persistent, but read-only memory, and it is used to store program data. So our program is stored in this flash. Then there's SRAM, 40 kilobytes in this case. SRAM is basically memory, main memory in the case of a desktop system. And it is read-write, but volatile. So whenever the microcontroller is reset,
anything stored here is lost. And of course, this will be used like it will in any traditional Rust program for storing runtime data. The stack and the heap goes there if you have one. An important thing to note is this is a lot less memory than what you're used to. We have 256 kilobytes of flash, which means our program can be no larger than 256 kilobytes. This is important. You have to keep in mind that you can't just unnecessarily bloat your program. You will hit those limits. And similarly, SRAM is also limited. So doing recursive functions that eat up a lot of stack space is probably not going to work. Having large buffers is difficult. As an example, I would not be able to store a full frame buffer for the display I'm using in this SRAM. There's just not enough of it here. And you have to design your software around those limitations, of course. Next to the CPU and memories, a microcontroller contains peripherals. Now, the CPU, as you can see, is not connected to the outside world in any way. It needs something to talk to other components of our system. And this is what the peripherals do. They are connected to the pins of the microcontroller and allow you to communicate with the outside world. So, for example, a USB device controller might be available, which you can use to build a USB peripheral that you can then plug into a computer. Or there might be an SPI or I2C bus controller, which you can then use to connect to other chips on your PCB to talk to them. Of course, there's many more peripherals available in a typical microcontroller than the ones I've shown here. In the end, when you build a project, you will choose the microcontroller depending on those peripherals. So you will choose one that has all the peripherals that you need for your embedded project. Now, all those peripherals and the CPU, they need to be connected in some way. And this is done with a bus network, also sometimes called the interconnect. In ARM CPUs, there is a single bus network. And in this network, you have a connection between the CPU and all memories and all hardware peripherals. And the microcontroller, so the CPU can then read from an address on this bus, and whatever is at that address will respond with the data for that address, or the CPU can write to an address on the bus, and whatever is at that address will respond by taking in the data and handling it. So as an example, for this microcontroller, this is what the addresses look like. So when we access an address that's in the range for one of the memories, this will behave as you would expect. You will read the data at that address in memory, or you will write to an address in memory. If you, on the other hand, access an address that's part of one of the peripherals, instead you're not accessing a memory, instead you're accessing a hardware register. And in these hardware registers, every bit has a special meaning. And when you write to such a hardware register, you do this to configure the peripheral. So for example, to change the speed at which a certain peripheral is operating, you write to a special hardware register at a certain address to set this configuration. And similarly, if you read from hardware registers, you can read back information from a peripheral. So for example, if some outside thing sends something to our microcontroller, we could read a hardware register to read this information. The important thing I want to note here is that it is a single bus network. And this means that accessing the peripherals and accessing the memories works exactly the same way. We can use the exact same software patterns for accessing variables stored in memory that we also use for accessing hardware registers. And this makes it very convenient. And even at a lower level, we can use the exact same instructions for both things. Okay, now embedded Rust. Why would we use Rust for an embedded system? First of all, Rust is a systems language, which means that it is built to be used in such environments. It allows you to have full control over what actually runs, so over what actually gets executed on the system, and there's very little inherent overhead to the language. So you can write your program to do exactly what you want, and you don't have to put up with limitations of the language, like, for example, a garbage collector or a higher level memory model, which doesn't allow you to perform low level accesses that you would need in an embedded environment. Next, the safety guarantees of Rust are very useful in embedded systems, especially. On such bare metal systems, we don't get a lot of the safeguards that an operating system provides. As an example, when you dereference a null pointer on an operating system, you expect to get a seg fault, right? On an embedded system, this might not be the case, because if you remember the diagram from before, actually the address 0 was mapped to flash, which means that if you dereference a null pointer, instead of getting an error, you silently dereference the first address of flash, which means you read back the first data from flash. And your program will happily use that instead of whatever the null pointer was meant to be referencing. So Rust can help you catch these kinds of bugs because you can't have a null pointer in Rust in the first place. And from my experience, this helps a lot because you don't need to troubleshoot as many memory and synchronization issues as you would have, for example, in embedded C. This is a whole class of problems that you can just eliminate by using Rust. Also, Rust's strong type system is very useful in this environment. The embedded Rust community is using this type system of Rust to build APIs that by design cannot be misused. So the idea is that if you were to try to do an incorrect hardware configuration, this is not possible at the type level. So you cannot construct a certain type representing hardware when you try to do it with the wrong configuration. Instead, the compiler will immediately refuse to compile your program. As an example, I will later show, you can enforce that you have the pins of the microcontroller correctly configured before you use a peripheral that wants to access those pins. Also, for embedded Rust, there is an existing ecosystem of libraries which help make your life easier, especially because we have Cargo as a package manager. This is much better than what people do in the embedded C space, where there is no such thing as dependency management. People just copy the source code of their dependencies into their projects, modify them, and it becomes impossible to update dependencies or to even keep track of dependencies. Next to the community, next to these libraries is, of course, a community. The embedded Rust community is very active, and they're very friendly people. So joining this embedded Rust space is very easy because people will help you on board a lot. And so even as someone completely new, I think you'll quickly find your way around. And last of all, for this project in particular, it was super nice to be able to use the same language on my target, so on the microcontroller, and on the host, which is my computer. I will show again later why this is useful, not only because it means I can stay in the same mind space of writing Rust code and working on both sides of the equation. Okay, first thing when doing embedded Rust in comparison to desktop Rust is this. Because we have no operating system, we cannot use the Rust standard library, and we have to use what is called no STD mode. No STD means that the Rust compiler will not try to link in the Rust standard library. Instead, we only get a subset of libstd, which is called libcore. Libcore is essentially a subset of the standard library, which contains only the parts which are OS independent, which means no things like file I/O or networking, because all those things require an operating system beneath. You also don't get, or at least by default, you don't get any allocator, which means you cannot use any of the allocating data structures from the standard library. So no vec, no hash map, no string by default. Instead, you have to use types which have a size known at compile time, so which do not rely on an allocator. This might seem like a big restriction, but actually this is usually what you want in embedded systems development, because using an allocator immediately brings a large number of problems with it. Because if you have very limited memory and you have an allocator, you might run into memory fragmentation further down the line, for example. And if you don't have an allocator in the first place, there is no risk of these kinds of problems. So a lot of embedded software is written to not even need an allocator at all. If you do want an allocator because your program has some complexity which doesn't avoid an allocator, you can, of course, define a custom allocator and then use the liballoc crate from the Rust standard library to bring back all those allocating data structures, like a vec or a hash map. And in parallel to that, there's also special crates which provide similar data structures to liballoc, but without the need for an allocator. So for example, there's the heapless crate, which uses statically allocated memory buffers instead of dynamic allocations. I want to now look at a hello world example of embedded Rust. The hello world in embedded systems is usually to blink an LED. And in embedded Rust, this might look like this. This is a trimmed down version. I will later show the full version as well. Let's go through the important parts to show the anatomy of an embedded Rust program. The first part is, you might notice the main function returns the exclamation mark. That is a marker which means that the main function will never return, and that the Rust compiler will verify that the main function can never return. So if you would now use a return statement in here, this would fail to compile. Then there's some initialization code. Essentially, we're booting the microcontroller. There is nothing running before our code runs, which means that we have to do all the hardware initialization ourselves. So this is the first thing you'll do in any embedded program. It is to set up all hardware for your application. And then you have a loop, which is the main loop, and it is an endless loop because, again, the main function never returns. And in there you have your application logic. So in this case, just set the LED pin high to turn the LED on, then wait some, set the pin low again, wait some more, and do this infinitely. Okay, I've skipped the initialization here. Let's look at that now. The initialization actually looks like this. What's happening here? First of all, the first thing is there is this attribute macro above the main function. And what this does is actually our main function cannot be the first thing that runs, because our main function is Rust code, and Rust code expects certain very low-level parts of the system to have been set up already, related to memory, essentially. And this is what this Cortex MRT entry attribute macro does. It essentially expands to all this initialization code, which is needed before our main can run. So setting up the lowest level parts of the system such that we can run Rust code. The next part is this. We call the peripherals take method. And this is something Rust specific. What we do here is we have this peripherals struct, which is returned by this method. This peripherals struct has a member for each of the hardware peripherals. And it kind of represents those hardware peripherals to our code. And each of those peripheral Well, representation objects, you can think of them guarding the addresses that we saw earlier for this peripheral. The take method now returns an option. It returns some the first time you call it and none for every future time you call it. And what this does is it means you can only ever acquire one version of these hardware peripherals. You can only ever have one object representing each of the peripherals. So each of them is a singleton, essentially. The reason we do this is as soon as you have one object in Rust, which you cannot clone, you only have one owner. And if you want to have multiple execution environments accessing this object in parallel, you must use proper synchronization. So some form of mutex to guard access to this object. So what we do here is by having peripheral objects only once and not being able to duplicate them, we enforce that a program must use proper synchronization to access any of those hardware peripherals. And this way, we, by design, prevent any kind of race conditions in regards to hardware access. Next, there's this clock setup, which just sets up the clock speed of our microcontroller, in this case to 16 megahertz. Then we set up a delay source. The delay source takes the clock speed information and takes a hardware peripheral for timekeeping, and then provides a facility to delay for a certain amount of time. And this delay is very simple. It just busy waits. So it is a while loop waiting for the time we want to delay for to run out. And the CPU does nothing else in the meantime. Finally, this sets up the LED pin, configures it into an output pin, so we can then set it to either high or low, so to turn the LED on and off. And again, here we use the Rust type system to enforce that the pin is in the correct mode before you can call methods on it. So to call the set high method on a pin, you must have first called some into output method before, which converts the pin into an output pin. And similarly, you could convert it into an input pin, and then you could call methods to read the electrical state of the pin. But you cannot use the output methods on an input pin then. And this is enforced at compile time. One more thing, Rust has panics. Normally, we have libstd providing a panic handler for our program, but in no STD environments, there is no libstd, so there is no panic handler by default, but Rust requires that there always is some panic handler to catch panics, which means we must declare a panic handler of our own. There are crates you can use for this. The simplest one is panic halt, which just halts the CPU when a panic happens, which you can import into your program by just using one use statement. There are other panic handlers available in crates on crates.io, so just search for panic dash and you will find a lot, which do different things. So for example, if you have a debugger connected, there are panic handlers which will output the panic message to your debugger so that you can then see it as a developer. Or you could have a panic handler that persists the panic message in some sort of memory. So you can then, when the system starts up again, read out this memory to find out what the reason for the panic was. Or, of course, you could also define your own panic handler, which is actually quite simple to do some custom thing whenever a panic happens. Okay, so this would be the full Hello World example. It is quite a bit more verbose than a Hello World on a traditional system, but that's because we're on such a low level that we have to do all those things ourselves. There is no outside system that can take care of this for us. Now, I've skipped over a little part here, which is we used some crates to access the hardware. Of course, these crates must be chip specific. And for most of the mainstream microcontrollers, they already exist. And there's multiple layers to these hardware support crates. There is the lowest layer, which is called the PAC, which stands for Peripheral Access Crate. And this provides register level access to the microcontroller's peripherals. So if you remember from the diagram before, a PAC provides essentially wrappers around all those addresses for the peripherals and some convenient accessors. So in this case, I was using the STM32F4 crate, which provides these register accessors for STM32F4 CPUs, but I wasn't using it directly. I was actually using it through a re-export. This PAC crate, this is usually auto-generated Rust code, which is generated from a, well, you can think of it as a machine-readable version of the datasheet for the microcontroller. So the datasheet contains tables of all the registers, and there is a machine-readable version of these available, and we use it to generate this PAC crate. So it generates an API for all those registers. This is a small example. So here we're accessing the CR2 register of the USART1 peripheral, and we're modifying some bits in this register. Specifically, there is a bit field, which means a number of bits bundled together, which represent the stop setting for the USART1, and we set it to the stop 2 setting. And as you can see, this PAC crate already contains definitions for all those values and bit fields and registers. And by using this instead of using the raw address and writing raw values into it, it's harder to do things wrong. So the PAC provides an API that makes it easier to do the right thing instead of having to continuously look at the data sheet and calculating the exact values that you need to write into a register. Of course, by being register level, there is no guarantee of semantic correctness here. So the code you're writing on PAC level, it might still not work because you might be writing to the registers in the wrong order, or you're setting the wrong values in some register, which in turn interferes with values in another register. There is a level on top of the PAC which takes care of that, which is the HAL. HAL stands for Hardware Abstraction Layer. And the HAL now provides high-level APIs for accessing the peripherals. The idea is that you cannot misuse a HAL crate. So if you were to try to do something wrong, this would fail at compile time rather than runtime. As an example, this would be code to set up a serial console. The first thing we do is we set up the pins for over which this serial console is supposed to talk. And the Rust type system is used here to enforce that the pins are in the correct mode before you hand them over to the serial driver. If you do not configure them in the correct mode, it would be a type mismatch, and the Rust compiler would refuse to compile this for you, which means that you can be certain if this code compiles that the pins are actually in the correct mode. And there's another thing here, another safety guarantee, and that's this serial new function. It actually consumes this USART2 type, which represents the peripheral, and it also consumes the pins. And it does this to take ownership of the pins and peripheral such that they are no longer available to be passed to any other driver, which means you cannot accidentally configure 2 drivers to use the same pins, for example, because they were already moved into this other type and as such are not no longer available, and the Rust compiler can check that you don't double use a certain type, for example. Okay, now let's actually look at this project I built. So this is again my Pavu mixer. It works roughly like this. I have this mixer. the mixer is then connected over USB to a host daemon running on my computer, and this host daemon talks to Pulse Audio on one end and talks to the mixer on the other end to manage data flow between the two. Specifically, Pavo Mixer and the host daemon, they talk over USB. For those that have any experience with lower level USB, I wrote myself a custom USB class here instead of reusing an existing one, not because this was a sensible thing to do, but because I wanted to play with the libraries for USB and Rust. For a real design, you would reuse existing USB classes. So for example, for this device, it would have made sense to build a USB MIDI device instead of some completely custom thing, because then you could also reuse other USB MIDI devices with the same code base. Over the USB connection, which is packet-based at this level, I used the postcard crate for serialization. Postcard is a Zerde serialization format, so you can just use the normal Zerde macros to do, and then serialize with postcard. And postcard is a very compact binary format, and it supports no STD environments, which makes it perfect for this use case. So I had these data structures, and because I'm using Rust on host and target, I actually put them into a crate. And this crate is then pulled in by both the firmware and by the host daemon, which means the exact same data structures are used on both sides. And this was one of the things that why it was so cool to use the same language on host and target. Because I was using the exact same code for this communication schema, whenever I did a change here, this change would immediately reflect in firmware and in the host daemon. So for example, if I would add a new host message here, the firmware would stop to compile, because in the firmware there's a match over this host message enum, and this match would now no longer be exhaustive. It would no longer match on all variants and handle them appropriately. So before I could continue, I would then have to build an appropriate handler for this host message, which means I cannot accidentally emit host messages which the target isn't prepared to parse. So I had to write some firmware on the target. This firmware has a very basic job. It should, on one side, wait for USB events. So if the host daemon updates some things, like for example, if a new application started up and opened an audio stream, it should send the icon for this application. And on the other hand, the firmware should wait for hardware events, like for example, if I move one of the faders or if I press a mute button, the firmware should react to that. So this can be boiled down into essentially a number of tasks that the firmware has to do. First of all, the USB receive task, which means receive USB transfers. So messages from the host. If a message arrives, update the relevant LEDs, update the display. Then there would be a mute buttons task, which reacts to a mute button being pressed. So this task does nothing until a mute button is pressed, and then enqueues this update notification for the USB host. Importantly, you cannot notify the USB host. This is a limitation of USB. Instead, you have to wait for the USB host to poll your device. So I would enqueue those and then have another task later, which would send them when the host polls us. Then there is a faders task, and the faders task just continuously reads out the position of all those hardware faders. And if I move them, it will check if I move them enough to warrant a message, and then it would also enqueue this message for the host. And then finally, of course, there's the send task, which sends out all those enqueued updates whenever the USB host polls the device. So here I have a number of essentially independent tasks, which each do their own thing and should run it essentially in parallel. So each do their own thing at the same time. How do you do that in Rust? Well, use async. This might seem a bit unusual, but actually you can use Rust async in no STD environments. This is one of the very cool things about Rust, is that its async framework is built in such a way that it does not depend on any kind of allocator and also not on any kind of host operating system environment. Instead, Rust async is just a set of mechanisms to drive a future to completion. Each future is advanced whenever you poll it to its next await point, and from there it then returns, waiting for some event, and then you poll it again, and then it continues, or it reports back that the event it was waiting for has not yet occurred. So this is perfect for the 4 tasks I showed. I can poll each of them, ask it, can you proceed? Or if it can't proceed, it will just return, say, no, I can't. And I can then poll them in a loop. So polling each one after the other. And this polling, this is done by an executor. As we saw in the previous talk, you could use Tokio, but of course, Tokio requires an STD library. It requires an operating system. Tokio is just not built for such environments. Instead, we need a custom executor which can run in no STD environments. And in this case, it doesn't need to do absolutely anything but just poll the futures one after the other. I'm not even using the concept of wakers here, if you know the details of async Rust. Instead, I just poll tasks in a loop. So even if the task doesn't have any work to do, it gets polled again. Of course, you could optimize this a bit to actually include wakers and only wake up a task when it actually has something to do. If the hardware reports back that something happened, you could then wake this task, and then the executor would only poll this task. But here, this isn't done. There's a simple crate which implements such a super simple executor, which is cassette. And this is what I'm using in this project. And here is an example of a task. So there's the mute buttons task, which again waits until a button is pressed and then enqueues this button update. And the way it does this, it's very simple. First, there is an interrupt pin. This pin signals that something happened to one of the buttons. And if this pin is low, it means that something has happened and we need to act on it. If it is high, it means nothing has happened. And so the first thing we do if it is high is to call this yield now function, which just means I no longer have any work to do. Please hand the CPU to other tasks now. So at this point, the executor would then start executing the other tasks in my firmware and only return here once it has polled them all. And continue then means that we jump back to the beginning to check again whether the interrupt pin is asserted. If it is, then I check each of the buttons. And if it is pressed, I insert an update into this pending presses queue, which is then picked up by the USB send task. And finally, after I checked all the buttons, I yield again, which means that now probably the USB send task can pick those up as soon as the host polls it again. And this is what async allows me to do with embedded Rust. Each of the state machines of my firmware becomes its own async function. And these are now independent of each other. The traditional pattern in embedded systems would be to have one big loop which handles all the state machines of my firmware at the same time. And this gets very messy because it's one big function, one big loop, hard to keep control over this. With async Rust, we can pull those apart, have individual functions for each of those state machines, and they get called by the executor to pull it all together again. To quickly show, this is how I would initialize the system. The first thing is initializing all the tasks. So first the USB task, then the faders task, and so on. And then I build a future that pulls all those tasks into a single future by using the futures future join macro. This macro essentially pulls all the futures one after the other. And because those futures all run infinitely, the futures join will also run infinitely. And then I hand this to the cassette executor, which means that cassette will now pull all those tasks one after the other infinitely. That's why the unreachable in the very end.
And there's a question.
Yeah.
The question is it possible to use RTOS, like free RTOS or ThreadX with embedded Rust? If yes, is it possible to use async Rust with RTOS tasks?
Yes, you can. Well, technically, you can use FreeRTOS. I think there are also some bindings available, although last I checked, they were not quite up to date. Especially because Rust integrates so well with C, it is very easy to build Rust into an existing FreeRTOS C application by just, for example, using one driver that's written in Rust and integrating that into an existing FreeRTOS application. Using async in this situation, I mean, it's possible, but you'd need to write an executor that integrates it somehow. Rust async tasks are completely separate concepts from tasks like they are in FreeRTOS. So FreeRTOS will have a separate stack for each task, while the async tasks of Rust, they all run on the same stack. And so I would say what you'd want to do is probably to have one FreeRTOS task which drives all the async Rust futures, and then have parallel FreeRTOS tasks for other things that cannot run from the same stack and FreeRTOS task. All right. Okay, finally, a few words about this host daemon. Again, it talks to the firmware, and on the other side, it talks to Pulse Audio, and it essentially has one job. Whenever the firmware reports that I've moved a fader, it will update the corresponding volume in Pulse Audio. And on the other side, if a new application opens a Pulse Audio stream, it will match this stream to one of the channels according to a configuration file, and then send the firmware that this channel is now active, which means the green LED on the board turns on, and it will also then send the icon for this application to the display. Demo time. Let's hope this works. So I start up the host. Actually, I can't because I have some UDEF rules set up to automatically start it in the background. Let's stop that and instead start it here. And you can see the first thing it did was it detected an existing stream from Lollipop, which is a music player, attached this stream to channel number 1. It then sent to the firmware an update, which means to send all the channel states, and then we got back the volume that the fader is currently at. It also sent an icon, which should be visible, but isn't right now. Interesting. And if I now move a fader, you can see that the firmware, the host daemon notices this. And if I were to look into Pulse Audio volume control, you could see that the software fader is moving alongside the hardware fader. All right. There isn't much more to show. That's it. Finally, if you have any questions, let me know.
Thank you very much.
Awesome, man.
Super talk.
Did you also design the PCB yourself?
Yeah, so in this case, it's actually, I can show, I think at least.
Can you repeat the question?
Yeah, so the question was if I designed the PCB. So yes, I did. I explicitly did not talk about it here, but I built myself a little PCB for the front panel. Can also be seen. Actually, yeah. Which houses all the components, and on the back side there's this pin header which I connect to a board hosting the microcontroller. And in this case, I reused an existing microcontroller board because right now those are much easier to get than CPU chips themselves. That said, for mechanical stability, it would have been much better to not have this cable inside the box and instead to have the microcontroller on the back of the board, for example. Yeah, but for this project, it worked out okay.
Do you transfer the icons when you use USB or just the name of the icon?
Can you repeat?
Do you transfer the icon itself? Or
yeah, so what I do is I use the GTK crate. So pulse audio for each stream reports an icon name. And then I use the GTK crate to get the icon for this name, because there's a free desktop specification for how to map icon names to files. And then I render this into a pixel buffer using Cairo. And then I send over this pixel buffer, which is then directly displayed on the target. Which also means, and I found this very cool, it automatically uses the icon theme I have on my desktop on the target.
And is it buffered somewhere?
Because
the memory was pretty small.
Yeah, right. I cannot store the full frame buffer for the full display on my target, but I can store enough frame buffer for a single icon. So what I do is I transfer the icon into a buffer, then write it out to the display and immediately forget this buffer for the next one. So at runtime, only the display itself remembers the icons.
But still there's this one step where you have to buffer it once for when you receive the package, right?
Yeah, I could write it directly to display, but the problem is then you would see the icon building up slowly, and it's much nicer if this happens at once.
Rendering issues.
Any questions in Discord?
And, another quick question is there anything, like you mentioned all the pros of using Rust for a minute, is there anything holding it back? Like you said, like can I use it for kind of every microcontroller on the market already? Or is there existing embedded C libraries? Because I mean, libraries can't be too big. Because
right. So it's a bit irritating that I hear myself. Can you maybe turn the volume down a bit? Or is it here? Oh, it is mine. I'm trying to blame you. Okay, 1 second. Yeah, actually, this should do the trick, right? The stream doesn't show up because I specifically removed Chromium from the mixer config before the talk, so it doesn't show up during the talk. So this is how it bit me. I could also press the mute button, and now it's also gone, I hope. Okay. What was the question?
The question was just, is there anything holding?
Right. So the question is, why not use embedded Rust? First of all, the ecosystem is still quite young. So the usual way you design embedded applications in the embedded C space is you get an SDK from the chip manufacturer, and this SDK comes bells and whistles included, which means a lot of libraries are already there. And you can immediately start working on your application. With embedded Rust, you'll find that for certain more complex things, you'll have to work on the lower levels a lot more than with C. So for example, if you were to want to have a USB host instead of a USB device, there's not that much Rust code available for this yet. So you would have to write that yourself first. While if you use an SDK from STMicro, for example, they already include libraries for that. But that said, it's the, come on, it can't be true. Failing to move to the other screen. Can I not mute it? I cannot mute it. Anyway, so, but that said, it's super easy to integrate existing C libraries into Rust projects. So even if you have something for which there is no Rust library yet, integrating existing C code is reasonably easy. Apart from that, you'll find that a lot of obscure architectures aren't well supported. So hot word from me, but for example, AVR is still very experimental in the compiler. So you'll find that on the Arduino boards, basic stuff works, but if you try to do more complicated things, you might hit compiler bugs. If you want to write production code, of course, this is a non-starter. So yeah, I think those are the two big things I'd say where Rust really doesn't fit. If you are convinced that Rust would be the better language to use in the first place.
All right. Cool. Thank you.
That's it.
That's it.